When we were looking at the different structural isomers, you may have noticed that we were forming structures that have branching. So here in black, this is what I refer to as the main chain. Or the parent chain. You're going to hear that term a lot when we talk about naming. In blue, we are representing a branch. And another name for a branch is a substituent. I use these terms interchangeably, so don't let that confuse you. Branches are substituents. So we're going to now learn about how we're going to name molecules that have branches, right? So the longest parent chain here is 5 carbons. 1, 2, 3, 4, 5. But that's not pentane, because notice that there is an additional carbon up here. And it's not hexane either, because it's not 6 carbons connected in a straight chain. So we need to have some way of naming these things. The thing is that you're going to see different types of main chains, and you don't want to have to write every single possible combination. So we're going to use the term R to represent the main chain. So the structure that I just drew, I could have drawn it as R with a little branch up top. So R really represents any hydrocarbon chain. So R could be pentane, it could be hexane, it could be octane, it could be any number of carbons connected in whatever pattern. So let's take a look at some nomenclature. Whenever an alkane chain is connected to something else, so this little group up here, because there's only one corner here that's representing one carbon, so really this is a CH3 group, we are going to call that an alkyl group. So alkane is telling us a bunch of carbons connected in by single bonds. An alkyl group is telling us that this is going to be an alkane that is connected to something else. So an alkyl group is a carbon branch connected to a carbon chain. And just like with all of the other organic chemistry naming, we're going to change the ending to represent the fact that this branch is attached to something else. And we'll use the same prefixes we have been using to indicate how many carbons are in that chain. So let's take a look at our alkyl nomenclature. You'll find that it's very repetitive. All right, so just like everything else, you're going to use your Greek prefix indicating the number of carbons in the branch. But in this case, instead of the ending ane, you will use the ending il or YL. And that's pretty much it. So let's say we have some main chain and there is a 1 carbon branch sticking off of it. This is exactly the example that we were looking at. So this is represented by R. And over here, we have a CH3 group, right? Just 1 carbon. Well, since this is 1 carbon, the prefix is meth. And then we'll use the ending il to indicate that this is a branch coming off of some main chain. So that becomes a methyl group. If we have 2 carbons connected to a parent chain, we'll call that an ethyl group. If we have 3 carbons connected to a parent chain, we will call that a propyl group. If we have 4 carbons connected to a main chain, we will call that a butyl group. And so on and so forth. So the same type of pattern that you've been seeing thus far. We could also represent these in a line angle format. So for methyl, it would just be a line. indicating that there's one carbon over here that I'm not showing. For ethyl, we would have a little curve over here. So there's one carbon here and another one here. In propyl, there would be 3 carbons. And in butyl, there will be 4 carbons. And I just want to reiterate that R can really be anything. So let's say I have a long chain like this, and then I have a branch sticking out. Well, this main chain over here is nonane, and then there is an ethyl group coming off of it. So this would be an ethyl branch attached to nonane. And we're going to take a look at a very systematic way of naming these. Now, before I get into that, you will see that once you have an alkyl group that has more than 2 carbons, so alkyl groups with 3 or more carbons can have structural isomers. So we can actually start to get some branching on the branches themselves. So you can get this really big tree-like molecule. And those branched structures are going to have their own names. So before I get into that, let's talk about how we're going to classify carbons, because this will help us make some sense of where are these terms coming from? Why are these branched structures called what they are? So we can classify carbons based on how many other carbons they are connected to. So I'm going to focus in on this carbon right here. And if that carbon is connected to one other carbon, so I'm focusing on this carbon in the middle, right here, the one in pink. If it's connected to one other carbon, then we call it a primary carbon. If we connect that carbon to 2 carbons, so this pink carbon right here in the middle is connected to 2 different carbons, then we call it a secondary carbon. If that carbon is connected to 3 carbons, then we call it a tertiary carbon. And finally, we can have a scenario where that carbon is connected to 4 carbons, in which case it has no hydrogens because its octet is complete. In that case, we would call it a quaternary carbon. You're not going to see too many of those in this course, but it does appear occasionally. Okay, let's take a look at the different branching that we can get on alkyl groups. So I'm going to take a look at propyl, and we'll look at structural isomers of propyl. Okay, propyl, just regular run-of-the-mill propyl, would look like this. There are 3 carbons attached in a chain. And we can also represent this in a condensed structural formula so you can see how these things connect. So there are 3 carbons connected to some R group, and this R group is just some long hydrocarbon chain. Now we can connect this differently. So in this case up top, all of the carbons were connected to each other. But I could have a scenario where I actually connect these to the main chain through the middle carbon. And then that's going to have a different name. I could also draw this in the condensed structural formula so you can see how these things connect. So the example up top, where they are all connected in a straight line, we call these propyl. In the example on the bottom where they connect through this middle carbon, we call that isopropyl. So this is an isomer of propyl. It'll be really important to know these. So all of the ones that I'm about to list, you will need to know. Let's take a look at some butyl structural isomers. Okay, our standard butyl will have 4 carbons connected to each other. And I could draw these in the condensed structural formula format. So if they connect in a straight chain like this, we call that butyl. But they can take on different structural isomers. So instead of connecting the main chain to the alkyl group through this first carbon, let's say I connected through carbon 2, and I get something like this. And I can represent that in a condensed structural format as well. So you may want to spend some time practicing converting these from line angle formulas to condensed structural formulas. Now in this case, I call this sec-butyl. And here is where the classifications of carbons can be really helpful, because you're going to see that these are going to have all kinds of prefixes. Notice that a secondary carbon is defined as a carbon that's connected to 2 different carbons. If I hone in on this carbon right here, notice that it's connected to 2 carbons. So this carbon in pink right here, that is a secondary carbon. And that's where this prefix sec comes from. This is telling us that the butyl substituent is connecting to the main chain through that secondary carbon. So these prefixes can kind of help distinguish between these different types of isomers. We can also have the butyl substituent connect through a tertiary carbon. So I'll expand this out so you can see how that actually connects. So notice that this carbon in the middle is connected to 3 carbons. And when we're classifying these substituents, the R group is actually a carbon, but we kind of ignore that. That's not included when we're classifying this carbon in the middle. So this is a tertiary carbon. So we're going to name this very creatively tert-butyl. Tert for tertiary. Some students have told me that this kind of looks like a chicken foot. So sometimes I refer to this as a chicken foot substituent, if that helps you remember it. Don't write chicken foot on exams, but if it helps you remember it, then that's fun. Okay. And the last one we will see is isobutyl. Now that prefix, unfortunately, is not super helpful. Iso is really telling us that all the carbons in the chain, except for 1, are connected in a straight chain format. That's maybe not super informative or helpful, but you can kind of see it kind of looks like isopropyl, right? Except there's 1 additional carbon right here. And I'll expand this out so you can see the connectivity there. Oh, I feel like I'm missing. No, I'm good. Confusing myself there. Yep, 4 carbons. Okay, so you can see we can have different structural isomers even within the alkyl groups themselves. There's another type of branching that you will see that does not involve carbons. So you can actually get halogen substituents as well. And those will have a different naming system. Probably easier naming system. So in that case, we're going to change the INE ending of the halogen to O. So if the main chain has fluorine attached to it, we call that fluoro. If a chlorine is attached to the main chain, we call it chloro. If we have bromine, that's bromo. And if we have iodine, we call that iodo. Once we actually start putting these names together, we're going to have to figure out how are we going to prioritize these. And I will say that halogens and alkyl groups have the same priority. Same naming priority. And I will show you in the next video how we're going to handle that and how we're going to put all of this together so that we can name compounds with